Welcome to Data Science 1, Probability, Variance Rules. Okay, we're going to need to know what a probability density function is and the expectation rules from the previous video. Somewhere in the back. Yes, previous video, I think. All right, so here are our previous rules that we came up with. The expected value of a constant is a constant. That should make sense. 5 will be 5 tomorrow. I would expect 5 to be 5 tomorrow. All right, if I have a function g of x and I multiply it by a constant, then the constant can come out. It just pulls right out of the expectation operator. And if I have two functions of the random variable, then the expectation can cross the addition. So it makes it quite easy to use. Now we want to find some rules for variance as well, and we'll talk about these, and I'll show you why they work, or at least most of the way in this video, and then the rest of the way in the next video. So the rules for variance. The variance of a constant is 0. That kind of makes sense. How much does a constant vary? It doesn't. 5 is always 5. It's not changing from 5 to 6 to 4 to 5 to 6 to 4. It's always 5. Here, when we pull out the variant, we have a constant inside there. We need to pull it out as a squared. Okay, and if x and y are independent, then the variance of x plus y is equal to the variance of x plus the variance of y. And we're going to play with that idea when they're dependent in the next video. So you'll just have to hold on to that. All right, so rule 1, where does this come from? Well, if you just play with it just for a second, you'll see that it's pretty easy to show that it's equal to 0, even though intuitively it should be equal to 0. So here I plug in c minus the expected value of c, which would be its mean, and then square it. Well, what do I know? I know that this is all a constant, so it can get pulled out. C minus c squared. Well, c minus c is 0, so this doesn't even matter. So it's 0 times anything else is 0. Done. This one takes a little bit longer. So here we have the variance of a constant times a function of x as the constant squared times the variance of the function of x. So we're going to start off the same way, c times g of x minus the expected value of c times g of x. Quantity squared, f of x dx. Then what do? I pull out the c here out of the expectation, just so you can see, pull it out of the expectation there. And then I notice that since it belongs to both of these, I can factor it all the way outside the parentheses here and get c squared. And then the c squared then comes out, and then I see, well, this just looks like the variance of g of x, and again, c squared variance g of x. Now here, this one is a little more complicated, and we'll talk about that more in the next video when we talk about covariance, because I think that it needs a video all to itself so you don't get completely lost. But this only works when they're independent. Okay, so let's look at the example we had before where we had x and y were independent, a, b, c are constants, and we have the expected value of x is mu of x, variance of x is sigma squared x, and expected value of y is mu of y, and the expected variance of y is sigma squared y. And we wanted to know before what was the expectation of this. Now we want to know what the variance is. And if you just start off here, well, if we said they're independent, that means we can break it across addition. So we go across addition, we use the next rule, pull out the constants, which are a squared and b squared, and we notice that we have a variance of c over here, and c is a constant, so that becomes 0. And then if I plug in what I know about what's the variance of x, I get sigma squared x plus b squared sigma squared y. And these rules come in super handy if you're a statistician, and if you're a data scientist, they might come in handy here and there. But if you're a statistician, you often run across things where you need to find the variance of something, especially if you're working with some sort of mixed effects model. But anyway, moving on. Okay, let's consider a real example where this might be an issue. Think about converting from Fahrenheit to Celsius, and the rest of the world goes, who in the world uses Fahrenheit? Well, it's us Americans. We use Fahrenheit for some reason. I don't know why. But anyway, we want to convert between the two, and we want to see how something would change in terms of the mean and the variance would change across this time, or across this conversion. Okay, so here's the formula. The Celsius is 9/5 of the Fahrenheit measurement minus 32. Pretty straightforward formula. Can't really do it in your head all the time. But anyway, it is there. So what we can do is we can find the expected value and the variance. So let f be the random variable measured in Fahrenheit with a mean μf and a variance sigma squared f. And let c be the corresponding Celsius measurement. What's the expected value of c? What's the variance of c? So if I do this, all I do is take my formula here, drop it in expected value, apply my rules. This 9/5 is a constant, so I can pull it right out. And then I know that expectation goes across addition, and so I can move this in and across addition, and this is what I end up with. 9/5 times the mean of Fahrenheit minus 32, which is kind of what you would have thought it would be, okay? But the variance is not, okay? So let's go do the variance next. So I do the same thing, variance here, this is a 9/5 is a constant. When I pull it out, I have to square it. So it becomes 81/25 times the variance of f minus 32. Well, this can go across addition because 32 is a constant, so it's independent of f. So we have the variance of f minus the variance of 32. Variance of 32 is a constant, so it's 0. So we end up with 81/25 times sigma squared f. Okay, so now we have our answers side by side here. It's the exact same slide as before where I had the question marks, but here we have the answers in here, and that might be a little bit different than you thought it would be. But anyway, this is the formula that works out. All right, so rules, variance of a constant is 0, and that should make sense. If I have a constant in here, when I take the variance, I pull it out squared because variance is really in squared units. Okay, and x and y are independent, then it'll go across addition. Covariance comes in the next video, and it's considerably more complicated, so we'll see you there.